Hey everyone, welcome to Driven Math and Physics. So today we'll be looking at a problem that involves internal resistance and Ohm's law. So let's get started. What we notice from the circuit diagram is that we're given a circuit that has three components that have resistance. So we'll label this one as resistance 1, this one as resistance 2, this one as resistance 3. The reason why we're labeling the bulb as resistance 3 is because it also has resistance in the circuit. Now, they're also telling us that the EMF of the battery is 24 volts. Okay, and then they have given us as well the internal resistance as 1.5 ohms. Okay, so given that, they're telling us to first of all calculate. We'll start looking at 2.3, calculate the effective resistance. So 2.3 says calculate resistance effective. Remember, when calculating resistance effective, we're simply calculating total resistance. Now here they're saying we should calculate the effective resistance across the 10 ohm resistor and the light bulb. So they want us to look at these two components right here. Alright, so to do that, remember, if these things are in parallel, it means we can simply use this formula. It says R2 multiplied by R3 divided by R2 plus R3. That's the formula for parallel circuits. And so from there, it will be 10 ohms multiplied by 15 ohms divided by 10 ohms plus 15 ohms. So from here, it will be 10 times 15 ohms squared over 25 ohms. This cancels with that. And 5 into this is 2, 5 into this is 5, 5 there 3. We get a 2 times 3 ohms, which gives us 6 ohms. That's the effective resistance across the resistor and the light bulb. And they're saying here that when the switch is closed, the bulb converts 576 joules of energy per minute. Okay, so that is, before we solve 2.4, they're telling us that the power across the bulb when the switch, this S1, is closed, is 576 joules per minute. But you remember power is in watts, so we need to convert the minutes to seconds. That will be 576 joules divided by 60 seconds. That gives us 576 divided by 60 seconds, giving us 9.6. Okay, so it's 9.6 joules per second, or 9.6 watts. Okay, so that's the power. And then 2.4, they're telling us to calculate 2.4. They're telling us to calculate the reading of voltmeter 2 when the circuit, when the switch is closed. Okay, so V2 here, there's a voltmeter here. So they want us to find out what the reading of that voltmeter will be when the switch S1 is closed. Okay, so that means current begins to flow. What will be the reading of that voltmeter? And how we do this is very simple as well. First of all, we know the power, this power that is moving through the bulb, and we know the resistance of the bulb. And from there, we can calculate the voltage. Once we know that voltage, it will be the same voltage across that resistor. Why? Because they're in parallel, and voltage across a parallel network is the same. So from there, we know that power is equal to V squared over R. So we need to make sure we make V the subject of the formula. If we do that, it will be V squared is equal to P times R, and this becomes V equals the square root of P times R. Okay, so from there, we need to substitute everything. So V will be equal to the square root of, the power is 9.6 watts multiplied by, the resistance is, for the bulb is 15 ohms. When you manipulate everything, you'll get a voltage of 12 volts. Okay, that will be your voltage. And you know that since V2 is in parallel to V3, therefore V2 equals V3 equals 12 volts. So we've calculated the voltmeter reading of the V2 voltmeter. Okay, so once we know that, they're telling us here in 2.5 to calculate the reading on the ammeter, So this is the ammeter right here. How do we find this? First of all, we need to to first of all calculate the actual voltage here, okay, when the switch is closed. Remember, when the switch is closed, the EMF will be reduced to terminal voltage because of the internal resistance in the battery. Once we know that, we'll find the terminal voltage. Once we know the terminal voltage, we'll subtract the voltage across here from the terminal voltage, and then that will give us the voltage across this resistor. Okay, and once we know those things, we can literally end up calculating everything else from there. Okay, so how are we going to find the reading on the ammeter? Okay, let's start now. So to look at the internal resistance formula, we know that EMF is equal to voltage lost plus the terminal voltage. Okay, so in this case, E will be equal to voltage lost is current times internal resistors plus terminal voltage. But what they want us to find is the current first of all. So before we do that, let's calculate the current. Now to calculate the current here, remember here we know that the resistance is 10 ohms. Okay, let me just remove this. Okay, so we know that the resistance here is 10 ohms and we found the voltage as 12 watts. Here we know the resistance is 15 ohms and we found the voltage as 12 watts. We can calculate the current on each. So I2 will be equal to V2 over R2, and this becomes voltage 2 is actually 12 watts divided by R2 is 10 ohms. That gives us what? 1.2 amperes. Then from there, I3 will be equal to V3 over R3. This gives us 12 watts divided by 15 ohms. This gives us 12 divided by 15 gives us 0.8. So that gives us 0.8 amperes. Okay, so we know here is 0.8, here it's 1.2. Okay, then you remember how current moves in a circuit. If the current is coming from there, that means we're talking about electron current. As it comes from there, once it reaches the junction, it splits. Okay, and once it splits, it comes back here, it meets again and continues that side. So we know that to find the current total, that is the ammeter reading, it will be equal to 1.2 amperes plus 0.8 amperes. This gives us 2.0 amperes. This is the reading of the ammeter. So we know the total current flowing through the circuit from there. Okay, now after finding those, let's remove this part. Okay, after calculating those things, we now need to calculate, according to 2.6, we need to calculate the resistance of R. And how we're going to do this is, first of all, we know the current flowing through this now, that is 2 amperes as well. Here is 2 amperes, here is 0.8, there is 1.2. So we need to calculate the voltage moving through there. And how we do that, we need to first of all find the terminal voltage. Okay, so remember, E is equal to I times R, okay, plus terminal voltage. This tells us that terminal voltage is equal to E minus IR. Okay, so the EMF is 24 volts minus 2 amperes times 1.5. Okay, that 1.5 is resistance, so it's 24 volts minus, okay, 2 times 3 over 2, it actually gives you 3 volts. Okay, so from there it will be 21 volts. This is your terminal voltage, okay, or the potential difference that flows, that is in the circuit when the switch is closed, when current begins to flow. Okay, so once we know that the voltage here, the voltage throughout the circuit is 21 volts, we need to calculate the voltage here. Okay, how to find that voltage is simply the terminal voltage minus the voltage across this network. Once we do that, we'll find the voltage there. So voltage across R will be equal to it'll be equal to 21 volts minus the 12 volts across that parallel network. Okay, so when we do that, it will give us 9 volts. Okay, let me just confirm this. That's 21 minus 12, that gives us 9 volts. Alright, so the voltage here is 9 volts. Now to calculate the resistance there, remember resistance is simply voltage over current. That's 9 volts divided by 2 amperes. That gives us 4.5 ohms. That should be your answer. So the resistance here is 4.5 ohms. Alright, so I hope you've been able to follow, but always remember, when the switch is closed, the voltage is no longer EMF. It has to be the terminal voltage, the one that flows when the current is flowing. Okay, that's the voltage that you read, the potential difference you read across the battery when the current is flowing. This happens because of the presence of internal resistance within the battery. So this is how you solve this. Thank you.